Today we're going to be talking about how to integrate a function that might look as simple as what we see on the screen now. X sine x does not seem to be that difficult a function to actually try and integrate. However, if you try to use any of the methods that we have learned so far, we do not have a way to integrate something such as this. So when we have this, we have to resort to other methods for finding the integral, or actually approximating what the integral might be. We've already dealt with some of those, so let's look at a couple of those. For example, if we wanted to integrate x sine x, this is the curve x sine x right here, and if we wanted to integrate it from 0 to 3, we could do that by using Riemann sums. And if you remember, we had left Riemann sums and right Riemann sums. The picture you're looking at here has drawn 4 rectangles, 1, 2, 3, 4, and they're all right Riemann sums and right estimates. And if we add these up, we would estimate what the area is. And we talked about how with that, if we put more rectangles in, see, like if we move it up to 25 rectangles, we get a more accurate picture of what that is. Notice that our integral up here has actually changed slightly, and the more rectangles we can actually put in, the more accurate the approximation would be. But let's go back and look at where we started at with just the 4 in there, and let's talk about some of the problems associated with that. When we look at this, there seems to be a lot of area that's not accounted for right here. But then at the same time, this area and this area and this area are overestimates. So it's very difficult to know exactly how good an estimate we have there. Well, we can also do a similar thing with left Riemann sums. Again, this is the same curve, x sine x. We have 4 intervals again, and we have 4 boxes. These are left Riemann sums. And the 4th one is actually down here. It's a rectangle of 0. So again, we can get a more accurate indication by putting more in there. But still, no matter what, we still have some area that's being left out. So until we can actually put thousands or maybe hundreds of thousands of rectangles in, it'd be difficult to get an exact answer. And in fact, you cannot get an exact answer. All you can do is approximation. So you're familiar with those 2 ways of approximating already. Today we want to talk about how to approximate using trapezoids. Now again, this is the same curve, x sine x. It's on a little different scale, so it looks a little different to you. But notice that this time, instead of drawing rectangles, we've drawn trapezoids. And we'll start looking at this trapezoid right here. We've got 2 sides, the left side and the right side, and we draw a connecting line segment between those 2. So we make a trapezoid out of this, and now we're going to find the area of this trapezoid. Now, as you notice, there's still some areas that are not completely accounted for here, but it's a much less area than what we were having before. And as we put in more and more trapezoids, you notice when we get up to about 10 trapezoids here, we have very little area that is showing up in here as unaccounted for, and we also have very little area outside of the curve. So this would be a better approximation than either the left or the right. And you see here we got to 3.09 with just 10 trapezoids here. So trapezoids is most often a better approximation than left or right. Well, let's take an easier example, and if you've got your notes, you can follow along with me, 34 numerical integration. Let's take an easier example than x sine x to start off with. And I've gone ahead and written out a lot of information here. I don't want you to focus on copying it down. Just try to listen and follow along, and hopefully we're going to come up with a formula that we can use most of the time here. First of all, let's talk about trapezoids. The fact that we're dealing with trapezoids, what does a trapezoid look like? A trapezoid looks like this top figure right here. We have a height, which is from one base to the other, and two parallel sides, the top one being B1 and the bottom one being B2. And the formula for finding the area of a trapezoid is you add the two bases together, you multiply it by the height, and divide it by 2. Well, if you look at our picture over here, our trapezoids are not laying down like this, they're actually turned up, so it's a little more challenging to look at. The height is actually this distance across the bottom every time, and the two sides are right here and right here on this particular one. So when we're looking at this first trapezoid here, the left side has a height of 0 and the right side has a height of this function value right here, and so forth and so on. So I've written out here how we would actually find the area of each of these trapezoids. The first trapezoid is 1/2. The first base would be the sine at the value of 0, x equals 0, plus the sine at pi over 4, and all of that multiplied by pi over 4. Pi over 4 is the distance from 0 to pi over 4. And we could figure out a number for that. But more importantly, I want us to write it all out and see if we can see a pattern to it. And if we look at the second one, we have a 1/2 again. The left side is sine pi over 4, that's this side here. The right side is pi over 2, this side here. And the distance between them again is pi over 4. The third trapezoid again has the 1/2, again has the pi over 4 for the height. The left side is pi over 2 this time, and the right side is 3 pi over 4. And finally, for the last trapezoid, trapezoid 4, it's 1/2, the sine of 3 pi over 4, that's this side, the sine of pi, which is going to be 0, times a pi over 4. So I hope as you've looked at it that you've noticed that each of these rectangles has a 1/2, each of these rectangles has a pi over 4. So if we're talking about saving ourselves time or not having to write down as much information, we could just take the 1/2 and the pi over 4 out and know we're going to multiply our final answer by that. Now I want us to look at what's inside these parentheses again. We have the sine of 0, then the sine of pi over 4, and then in the second one we had the sine of pi over 4 again. So the last one in the first rectangle right here is the same as the first one in the second trapezoid. The last one, pi over 2, is the first one in the next one. The last one, 3 pi over 4, is the first value in the next one. So when you look at this, you'll see that many of our function values are repeated or duplicated. We've got pi over 4 twice, pi over 2 twice, 3 pi over 4 twice, and sine of pi and sine of 0 are only once. So if you're looking at it strictly from a graph standpoint, we're going to use the first one time, each of these inside of it, the pi over 4, the pi over 2, the 3 pi over 4, 2 times, and then the final one we'll only use again 1 time. And when we're trying to estimate the entire area, we're going to find that by adding these 4 up. So we could just as simply have done this by taking out the 1/2 and the pi over 4 and then writing down our function values. The first one, sine of 0 once, the next one twice, sine of pi over 4, the next one twice, sine of pi over 2, the next one twice, sine of 3 pi over 4, and the last one, sine of pi, only 1 time. Well, how do we know what these function values are, and how do we know when we stop? Well, we know we're going to start at the left side, that's our 0, and this height is how much we're going up by each time. So since we started at 0, 0 plus pi over 4, that's going to be our next function value, and we'll use it twice. Then we'll add pi over 4 to it and get 2 pi over 4. We'll use it twice. We add again 3 pi over 4, and we'll use it twice. And we'll add again, and we get the sine of pi. Now how do we know to stop at the sine of pi? Again, looking at our graph, we're stopping at pi, so that's the last one. It's only going to be used 1 time. That sounds very complicated, but if you'll scroll down to page 3 of your notes there's the trapezoidal rule written out in very generic terms. Now notice we've got b minus a over 2n. Where did that come from? Well, let's scroll back up to the first page. b minus a over 2n. Well, here's the 2, the 1/2, that's the 2 in the bottom. And b minus a is this endpoint minus this endpoint, pi minus 0, divided by n. How many trapezoids do we have? We have 4 trapezoids. So we can put in, for that formula, we get b minus a over 2n for our formula. Then we start with the first function value. Remember, this first function value will be f at a, whatever that is, and then it'll be 2 times the next function value. How do we find this next function value? We're going to take whatever b minus a over n is, without the 2, b minus a over n, and add that to this function value. We'll put that in here, and we'd evaluate the function, multiply it by 2. Continue that process until we get to the last function value, which would be b, and we'll use it only one time. So let's take another example and look at it. We're going to omit Simpson's rule for right now. And let's move on to this slide, which is slide 5. And we want to use Simpson's rule to approximate it. Actually, it's the trapezoidal rule, not Simpson's rule. We're going to use the trapezoidal rule to evaluate 0 to pi of the sine of x. Now, we just did this for 4. This time we're going to do this for 8. Okay, so if we go back and look at our formula, it's b minus a, that's pi minus 0, over 2 times 8, because we're doing 8 of them. That means we've got pi over 16. So this value out here is the pi over 16. Now remember, we said we'll always start at the a at this point here, so we'll evaluate the sine of 0. And then it's 2 times the sine. How far up do we go? It's b minus a, pi minus 0, divided by 8, because that's how many we're using. So we'll go to the sine of pi over 8. We'll evaluate that times 2. The next one, we add pi over 8 plus pi over 8. We get 2 pi over 8. The sine of that times 2. The next one, 3 pi over 8. Again, just by adding pi over 8. Times 2. And we continue with this process. 4 pi over 8, 5 pi over 8, 6 pi over 8, 7 pi over 8, 8 pi over 8. When we get to 8 pi over 8, we realize that's pi. We look back, that is our top limit of integration, so we'll only use that function value one time. And if we calculate that out, we will get an approximation for what the sine of x is if we integrate it from 0 to pi. It should be very close to 1, if I'm not mistaken there. So you'll want to be getting close to that. I recommend that you actually write this out and be sure that you understand how we got to this point for this particular problem. Now, another way we can use this is when we're not given a function. If we're just given a graph like this one that you see here, and we're asked to approximate the area using the trapezoidal rule. Again, we're not worried about Simpson's rule now. Using the trapezoidal rule for n equals 8. Well, if we look at our graph starts at 0 and ends at 8. So remember, our number out front is b minus a over 2n. 8 minus 0 is 8 over 2 times 8. That gives us 8 over 16 is 1/2. So we'll have 1/2 there. Then inside our parentheses, we're going to look at our function value at the very beginning of it. It's 0. How far up are we going to go? Well, it was b minus a over n. 8 over 8 is 1, so we're going to go up 1. What's the function value there? I estimated it to be the number 1. If you estimate it to be a little bit more, there's nothing wrong with that. Just write it down. And we're going to multiply that one by 2 because it's one of our inside function values. And we do the same thing. The function value at 2 is 3, so that's how I get the 2 times 3. The function value at 3 is about 6, so that's how I got the 2 times 6, and so forth and so on. 4, the function value is 9, so I have 2 times 9. 5, the function value is 10, 2 times 10. 6, the function value is 9, 2 times 9. 7, the function value I estimated at 6 is 2 times 6. And 8, the function value is 0. Now, why didn't I multiply the 0 by 2? Because it's my last one. If you'll look in here, you can count up inside the parentheses. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 values. We had an n equals 8, so we should always have one more value in here than what we had as far as the number of regions. We had 8 regions, so we should have 9 numbers, and we used the first one only once and the second one only once. So that's using graphs how you can actually estimate. One final way that we'll estimate is when we're given discrete data. So for example, this came out of a textbook, and we are told that the x values, the y values at these particular x values are these approximations, or these numbers. And we want to approximate the area of this. Well, we can figure out how many of our how many trapezoids do we have here. And if we count them up, we will see we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 trapezoids. So it's the rightmost x value is 1,000 minus the leftmost is 0 divided by 2 times 10, because we have 10 trapezoids. That gives us a value of 50. So that's what we're multiplying by on the outside. Remember, we expect to have 11 values on the inside of our parentheses. If we go up here quickly and count, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's what we expected. We'll use the first one once, the 125. Each of the next ones, all the way up until the last one, we'll use twice. That's how I got the 2 times 125, 2 times 120, 2 times 112, and so forth and so on. And the last one we'll only use once, and that would be the 0 here. And if we go through and approximate that, we get 89,250. I recommend that you go back and try to work these problems on your own. You can come back and look at this video and be sure that you got the correct answer, or that you're working in the right direction. This is not a very complicated process, but you do need to be able to do it, because it will be included on your next test.